You've probably been here before. You take a photo in a dimly lit room. The result comes out dark and full of static. So you tap that little wand icon on your screen, and instantly the image clears up. It feels like the phone analyzes the bad parts and paints over them with better colors. But there is no paint involved. It is entirely mathematical. To a computer, a digital photograph is just a grid of numbers plotted at exact coordinates. Each holds a value representing visual intensity. To make data suitable for human eyes, an algorithm runs rapid calculations on those numbers, swapping old values for new ones. How the processor decides which formula to run depends entirely on scale, specifically how closely a single pixel needs to look at the pixels right next door. To see how millions of pixels are rescued in a fraction of a second, we have to start at the absolute smallest scale possible and work our way up. The most direct level of image manipulation is a point operation, sometimes called an intensity transformation. At this scale, the calculation only tears about one thing: the target pixel's own original numerical value. It completely ignores every other pixel in the surrounding neighborhood. When you drag the brightness slider on your screen to fix a photo that is universally washed out, you are applying a point operation. The exact same math hits every individual pixel blindly. Curious. This chart is a histogram showing the distribution of gray levels in an image. If a photo lacks contrast, all the data points clump together. A specific point operation, called Histogram Equalization, takes those clumped pixels and forces them to spread out evenly across the entire axis. By mathematically forcing this uniform distribution of gray levels, the darkest darks and lightest lights are restored, instantly recovering the lost contrast. Point operations are incredibly fast. But because they execute in total isolation, they are completely blind to the broader context of the picture. To fix more complex issues, the algorithm zooms out slightly and uses a spatial filter, which is often referred to as a mask or a kernel. Instead of acting alone, a pixel's new output value is now determined by combining its original number with the values of a surrounding grid, typically a 3x3 block of its immediate neighbors. Giving the software this localized awareness is exactly how a computer identifies and removes camera sensor grain. A stray pixel caused by digital noise will have a wildly different intensity compared to the pixels touching it. A smoothing filter, like Gaussian smoothing, scans the grid, detects that extreme variance, and averages the numbers out, pulling it back in line with the rest of the neighborhood. Sharpening filters run the exact opposite routine. They scan the neighborhood looking for subtle differences and intentionally amplify them. When an image has low definition, blurry transitions lacking clear contrast, like the soft edges of this text, a sharpening filter targets those specific zones to eliminate the blur. Because spatial filters check the surrounding data before acting, the software makes contextual decisions, repairing targeted areas instead of sweeping blindly across the whole file. At the absolute highest scale, we stop looking at individual pixels and start combining completely separate full-size grids through arithmetic or logical operations. Think of merging two photos together to create a double exposure effect for social media. You are taking the values at pixel 00 in the first image, combining them with pixel 00 in the second image, and storing the result in a brand new file. But this requires strict alignment. The origin coordinates of both starting images have to map perfectly onto one another. If the two grids are different sizes, the math forces a compromise. The resulting combination automatically shrinks to the minimum shared width and height of their overlap. Once combined, the new pixel totals often exceed the format's maximum allowable limit, so the software scales or clamps the numbers to keep them strictly within a valid, displayable color range. We scale from the isolated adjustments of the single pixel to the contextual awareness of the 3x3 neighborhood, all the way up to macro grid arithmetic. This exact same spatial domain mathematics powers much higher stakes technology. Mastering these localized grid calculations is what allows deep space satellite arrays to cut through atmospheric haze and medical imaging software to enhance the subtle edges of an X-ray. It is the core mechanism that teaches a computer how to accurately see and measure the physical world. Every time you drag a slider to apply a filter on your phone, You are commanding millions of these micro-mathematical equations in real time.